Okay, so I am going to as I posted online, my last recording didn't turn out very well. The audio was terrible. So I'm just doing this one more time. Hopefully, I think this will come out better. Okay, so we're going to talk about a selection sort problem, then I'm going to talk about shell sort. So there's a worksheet, a selection and insertion sort worksheet that I posted online. Let's look at problem number 5. And so this is a little bit different. So what selection and insertion sort do is that they sort from smallest to largest. So it sorts in ascending order. So, and what it means for one object to be bigger than another is up to us. So numbers, okay, that's kind of, we know 1 is less than 2 is less than 3. And strings, if we use the built-in compare to method for strings, it actually sorts by ASCII value. So if it's all alphabetic characters in the same case, it's dictionary ordering, where like a word that starts with A would be less than a word that starts with B, but it has to be the same case. So for 5 and 6, I used a different criteria. Let's use the length of the string. And the greater the length, the greater the object. And the important thing is that the contents do not matter. And I've given this problem in the past where students kind of, well, if the string lengths are identical, well, then they start comparing the contents. So what I'm saying is we don't care about the contents, that like that word TWO is equal to ACB. The only thing that I care about is that the length is equal to 3. So 2 strings with the same length would be considered to be equal. So when we're searching for the next smallest, isn't that what selection sort does? It scans the rest of the array for the next smallest, and it finds the first one. And it puts that in, and it puts it into its proper place. So, let's just try this problem. Okay, so this is number 5. We're sorting house, door, 2, ACB, cat, the word TOO, and bring. And so length equals the length of the array is 7. Okay, so we want to find the absolute smallest. Well, the absolute smallest is that word TWO. There's 4 words in there or strings in there whose length is 3. So we look for the first one, right? So index smallest will be equal to 2. And then later on, we check, well, is TWO less than ACB? It's not, they're equal. They're equal. So or ACB is not less than TW, because in this case, we're not looking at contents, we're just looking at number of characters. So it turns out the absolute smallest, as we go from left to right, the absolute, it won't be the absolute smallest, but the first, there's 4 that are length 3. Well, we use the first one, that's TWO. So we exchange TWO, and in the first iteration, in house. So that's what happens in the first iteration. Okay, so now after the first iteration, we're guaranteed that the array, that the smallest element is at position 0. And now we scan the rest of the array and find the next smallest. Okay, so now we're going to scan door through bring and find, let's see the next smallest. We'll just do one more iteration. Well, in this case, the next string of length 3 is ACB. So notice how we exchange ACB and door. And then again, then the next iteration, we exchange cat and house, and then 2 and door again. But so once again, at no point do we ever consider the contents. And the same as in 6. It's the exact same problem, only with insertion sort. Okay, so I just wanted to go over this. We didn't do this in class, and but I don't think it's really that hard. Okay, anyway, you just have a different ordering criteria. Okay, so I'm going to stop sharing. And now let's get on to a totally the last topic. Not for the whole course, maybe for the test, I guess. Okay, so let's share the screen again. And so this is actually in your, there was a Zybook assignment on this. So it's shell sort. So shell sort is not actually a PowerPoint slide. I created this Word file. And shell sort, all it is a variation of insertion sort. It's a generalization of insertion sort. So insertion sort takes it, let's say like a number or like a string or some kind of object and looks directly to the left. And if the value to the left is greater, there's an exchange. Because again, we're going to go from smallest to largest. So that's what insertion sort does. It looks directly to the left, and if the object to the left is smaller, there's an exchange. And you keep looking to the left until you can't do any more exchanges. Either the element to the left is greater or equal to, or you're at position 0 and you can't go anymore to the left. Okay, so let's just look at this great quote from the Zai book. Shell sort is a sorting algorithm that treats the input as a collection of interleaved lists and sorts each list individually. Well, it says with a variant of the insertion sort algorithm. Okay, but basically, it's just so what you have is you have like an array here. So in this case, I have this array, and I think it's of length 16. In this example, the first number is 6, and then 7, and you can see here that the background colors are different, and it changes every 4th cell. So the orange cells are in 0, 4, 8, and 12. And then the blue cells are 1, 5, 9, and 13, and so forth. Then the yellow, like 2, 6, 10, and 14. Okay, so, and so what we do is we're just going to apply, so we have these, basically you have 4 individual insertion sort problems. Like the orange group makes up 1, the blue group makes up 1, the yellow group makes up 1, and the white group makes up 1. And the book talks about a gap. And so there's actually a gap of 4 in between cells of the same background color. So let's say like the 2, which is at array index 4, well, how much, if we go to the left, how far would we have to go? We have to go 4 to the left. At 10, which I guess is at index 5, well, how far would you have to go to the left to find the next blue one? You have to go 4. So the distance between cells of the same background color is 4. So we see the gap is 4. The gap can be anything we want. We choose the gap. But in this case, we have a gap of 4. And so, as I said, we're going to sort each individual list with insertion sort. Now it's not going to be sorted, right? But what it is, it's more sorted than it was before. The larger values are to the right, and the smaller values are to the left. And then what you do is you just apply the same process again. Now we can make the gap equal to 2. So then you only have 2 background colors. And then eventually, you're not guaranteed it's sorted until you just do regular insertion sort. At some point, you have to have a gap of, that's what insertion sort. Insertion sort is shell sort with a gap equal to 1, where you look directly to the left. Okay, so let's just see what happens here. Okay, so we have these interleaved lists. So step 1, let's see if I can make this bigger. Step 1, we sort the numbers in the orange cells with insertion sort, and then the blue cells with insertion sort, and so forth. We have 4 steps. So let's just go through one of the colors, the orange ones. Okay, so what numbers are in the orange cells? Well, it's 6, 2, 1, and 5. Okay, so if we're just going to do regular insertion sort, well, what would we do? We'd actually, so remember what insertion sort does? It's gradually building up this sorted list. It sorts the first 2, and then sorts the first 3, and then sorts the first 4. So if all we do is consider 6 alone, let's say, well, let's just pretend that array only has 1 element. It's automatically sorted. An array with 1 element is already sorted. So we're going to, okay, well, let's just pretend this array has just 6 and 2 in it, and let's sort it. So we compare the 2 and the 6. 2 is less than 6, so we exchange. But in this case, when we exchange, we don't exchange 1 to the left. We exchange 4 to the left. Okay, so that's what we have to remove the 2. The 2 and the 6 jumped 4 elements. The 6 to the right and 2 to the left. Okay, and so here is what happens after the first exchange. Okay, now we want to put 1 in its proper place. Well, you compare 1 and 6. So you're at this 1 and you go 4 to the left because you want to only compare numbers in the orange cells. And you compare 1 and 6. 1 is less than 6, so we exchange the 1 and the 6. Oh, but we're not done. You keep looking to the left until either 1 or 2 criteria. You go over the end of the array, or the element to the left is less than or equal to. Okay, well, 1 is less than 2, or 2 is greater than 1, so we do an exchange. So now the 1 is at position 0, And this is what I'm saying. You can't go to the left anymore. You can't go 4 to the left anymore, so you stop. And then, okay, so then the first 3 would be sorted. So now we have to put the 5 in its proper place. So we start at 5, we go 4 to the left, you compare it to 6. 5 is less than 6, so there's an exchange. And then we look one more time, 4 to the left. 5 is greater than 2, you stop. And if you just look what's in the orange values, it's 1, 2, 5, and 6. And so they're sorted. So if we start from position 0, every 4th element is sorted. Okay, so that's what's happening. And so the implementation in the book does kind of one background color at a time. There's different implementations. I've seen implementations where, well, let's do an orange. Let's like put the 2 in its proper place. Or then let's put the 10 from the blue list, and then the 10 from the yellow list, and the 22 from the white list. So we take turns one at a time. Okay, but that's not how they do it in the Zybook. Okay, so now if we actually sorted now let's say we sorted each list. Let's everything below here now. So let's say we sorted each list. This is how it would look. It's the top of the second page. And if you look, every 4th value is sorted. If we look at the blues, it's 7. And then we go jump 4 to the right, we get 8. Jump 4 to the right, you get 9. Jump 4 to the right, you get 10. So that's one way how you know that your answer is correct, or it's a kind of a, maybe a negative test. It should be sorted every 4th value. And if it's not, you made an error. And I know sometimes in class I've done this and I'm writing my answer. Oh, there's obviously an error because it's, in this case, the gap is 4. So it should be sorted in ascending order every 4th value. So, okay, so, but also notice it's not sorted. So again, if you really want it sorted, but what we do know, again, we move the larger values to the right and the smaller values to the left. And now you can apply shell sort again. Now just do a gap of 2. So you'd be comparing 0, 2, 4, 6, 8, 10. I mean, those are the indices. So you'd be comparing every other one. Okay, so you can have a gap of 2, or you can go just directly to a gap of 1, but it's not going to be sorted until you actually do the regular insertion sort where there's a gap of 1. So now the book actually has the pseudocode. I'm not sure if I put it in here. I thought yeah, here's the pseudocode. So I pretty much copied this from the book. And so the book doesn't actually have Java code. It has the pseudocode that we can convert to Java code. And okay, so numbers in this case is the array. Number size basically tells you the number of array elements. Okay, so when we're actually implementing the Java code, we really don't need this because we know that we know the length of any array. But this does make it a little more general. You could say, okay, let's just sort half the array. Let's just ignore everything. I'm not sure why you just want to sort half of it, but you could make it general enough so it's only sorting part of the array. Okay, start index, that's the initial index of the, of the gap. So like for the orange example, like for our example above, first of all, I should say, this code is just sorting one of the lists, one of the interleave lists. So this is what we do to sort the orange cells or the blue cells or the yellow cells or the white cells. So for the orange cells, start index would be 0. I have it down here. And then for the blues, the start index would be 1. And then the gap just tells you the distance between cells of the same color. And this is basically just, if you look at this code, it's just a generalization of insertion sort. What we're doing is that we're starting at I equals start index plus gap. And so let me just, in this case, for my example, the gap was 4. And if we look for the orange, start index is 0, and the gap is 4. So we're starting I out at 0 plus 4, which is 4. So what it would be saying is, let's start by putting that 2, the 2 that's in the orange cell, let's put that in its proper place. We wouldn't start at the 6 because once again, first we're going to sort the first 2 orange cells and the first 3 orange cells and the first 4 orange cells. If it's just one orange cell, it's automatically sorted. So we're going to start at 4. Let's go back to the pseudocode. You start at 4. Is it greater than are you greater than the first index of your particular background color? And then you check to see, oh, if I go 4 to, is numbers of j less than numbers of j minus gap? So if I go, is numbers of 4 less than numbers of 0? And if it is, you do the exchange. And so insertion sort, instead of the gap would just be 1. Wherever you see gap, you would just have 1. Okay, so so that's how we sort. So this method here, insertion sort interleave, sorts one of the back. That's how we sort one of the lists. And then we actually want to apply. And then the shell sort algorithm, which we see here on the second page. Okay, what it's doing here, it's actually calling that inner sort. This method insertion sort interleave gap number of times. The one thing I will tell you here is there's this, we're passing in this array called gap values. So shell sort, you can actually pass in you pass in all the gaps that you want to apply to this problem. So gap values could be, so let's say we want to have initially 4, a gap of 4, and let's apply shell sort with a gap of 2, and then the last one better has to be 1. If you don't have a gap value of 1, you're not guaranteed to be sorted. And so then it says for each gap and gap values, and then in the inner for loop, it's just applying that gap value to each one of the individual lists. So okay, so, and again, I think you really have to read this yourself. Again, just me talking about, hopefully my talking about it is clearing some of it up. Until you actually struggle with it, it can be hard to read. I do actually have the, I actually did put the actual code online. I implemented this. I'm going to stop sharing. I'm going to share again. And then, I have the, okay, so this is actually, I just put this online last night, so of course I should have been a little more prepared here. Let's see here. See, it kind of looks like, if you look at my project name, it kind of makes it look like I'm organized, but believe me, I'm not. Okay, so like what project holds the file I want? Yeah, so luckily, yeah, so shell is actually in the sorting project. It doesn't always work that way. Sometimes it's from some project for Math 130. Okay, so anyway, so here's shell. I have put this online. Okay, so, and I put a little bit more in just for some debugging statements or just see how things are changing as we call every iteration. So for this particular problem here, I just have a gap value of 3. So I'm actually not sorting it, right? Because gap value of 3 will be every third one that's sorted. So when we're done, so like the first index, like if it's a gap value of 3, I'd be sorting what's at position 0, 3, 6, 9, and 12. I think I typed this in yesterday. Yeah, and then for the second list, we started index 1. In the third list, we started index 2. And so let's actually run this and see what happens, since I probably have forgotten at this point myself. Okay, so yeah, so the array before calling shell, so those are the numbers in the original order. And now look, it should be sorted every third value because our gap was 3. Okay, so like 3, and then you go 3 to the left, there's 4, and then you go 9, and then 26, and then 27. So you're gonna have, so you kind of have to try, and hopefully those are the numbers in the starting for every third value starting at 0. And I think, so you have 26. I look in the original list, 26, 4, and then a 3, and a 27, and a 9. And yeah, we sorted those now. Those numbers are sorted every third value. So you can verify that every third value is sorted. And every value is stated in its appropriate list. All the list that starts with 0, all those values are still in the list that started 0 after we've run this. So here, let me close this. But anyway, you can see here, students, I did actually, so and students, so I did implement the code, right? So this shell sort, here's the array, numbers is the array you want to sort, and that gap values, is just an array of it's just the array of gap values that you want to apply. So I said, if you have a gap to sort it, you can actually put a gap value. The last gap value has to be 1. Okay, so that outer loop now, because the length of gap values is 2, that outer loop would iterate twice. So first we'd apply insertion shell sort for gap equal 3 and then gap equal 1. Let's try this. And it should now be sorted. If it's not, I'm going to be sad. Yeah, and you see now it's sorted because it put a gap value of 1. So the second time we call shell sort, it's really just insertion sort. And the gap value is 1. Shell sort is insertion, the regular classic, famous, the super famous insertion sort algorithm. So students, I guess I could ask there's any questions, but I'm the only one here. Okay, so one more thing, students. Okay. Let's look at the shell sort worksheet. Let's just go right to the solution. And so, so what do I have here? Okay, so consider the array. Okay, so this is how, if I was going to do this, I tried to do this on Monday's class without, without writing this this table right here, and I really messed up. And the thing is, it can be hard to see, like there's 2 4s, which the first 4 is at 0, 3, index 3, and the second one's at 4. I kept messing up, just kind of reading it and trying to count in my head. It's easy to lose your place. Like what index is that 8 in? So so this is how I used to do it. If I was teaching in a classroom, this is what I would do. I would actually create a table. I think if I was giving like a proctor test, this is what I do. I actually give the students this table so there's no problem in knowing, oh, that 6 is at index 5. But you create a table, and now the gap, I'm saying let's have a gap value of 3. So if the gap value is 3, so we're going to sort the values stored at indices 0, 3, 6, 9, and 12, and 1, 4, 7, 10, and then 2, 5, 8, 11. And here are the values in each of the interleaved lists. So the first one, we can see it's 20. So every third one, starting from 0, it's 26, and then 4, and then 3, and then 27, and then 9. All right. Let's do it for this one here. So we want to sort these values with the regular, we're going to use that insertion sort now. Except now we have to go 3 to the left when we want to put an element that says proper place. Yeah, so the first thing we would do is, you would compare, you start at that 4 that's at position 3, and you look 3 to the left, right? So you compare the 4 and the 26. 4 is less than 26, so you would exchange. And then you do the same for the 3, and then the 27 and the 9. Okay, but I don't actually have to use insertion sort. It's so small, I can sort this in my head. So after you sort each list, the first list, it would be 3, 4, 9, 26, 27. Okay, so then how do I actually write out the sorted list? Okay, so we sort the lists. And so we start here at the, where's the sorted list? Okay, so here's the sorted list right here. After we sort the individual lists, it's what's in red down there, sorted values for each list. So for list 1, it's 3, 4, 9, 26, 27. And then for the list 2, it's 4, 5, 7, and 8. And list 3, it's 1, 2, 6, and 10. And what you do is you just go down the columns, right? We'll take one from the first list, one from the second list, one from the third list, and then you go back to the first list. So I just go down the columns, 3, 4, 1, 3, 4, 1, 5, 4, 2, 9, 7, 6, 26, 8, 10, and then 27. And it's sorted every third value. It's not sorted, right? 9 is not less than 7. You'd have to apply this whole algorithm again with the gap equal to 1 to guarantee that it's sorted. And we might get lucky and it might be sorted, but that's luck. It's certainly not guaranteed to be sorted. So if I was going to do this in class, if there's like a proctor test, I'm sitting staring at you and making you nervous. No, I didn't do that. But if you had to do this, no, this is how you would do it. Okay, so now what is B? Okay, so let's look at the what's B? Okay, how many exchanges are required to put 3 in its proper place? Well, this requires a little more critical thinking. Basically, you just have to look that 3 is actually at positions at index 6, so it's in that first list. So basically what you can notice is how many values. So here, so let's look at, here's that 3 here. This is the 3 we're talking about right here. How many values to the left are greater than 3? Well, there's 2, it's 4 and 26. So there's going to be 2 exchanges. There's going to be 2 exchanges. By the time we, now I'll just say one thing, since by the time we sort, what would the list look like? It'd be, by the time you put the 3 in its proper place, the list is going to look like this. The list one, the first list would look like this, 4, because we would have exchanged the 4 and the 26. But it doesn't matter, right? They're still to the left of 3. And so we don't really actually, I've seen students do this. I say how many exchanges, and they actually go through all the steps of shell sort. You don't really have to do that. You just have to count how many are greater than 3, right? Because you can sort 4 and 26, but there's still going to be left of 3. Okay. Okay, so and basically you can do the same thing for the other values then. Like I said, how many to sort 8? Right, so if you look at that 8 in list 1, both values to the left of 8 are less than 8. So 8 there'd be no exchanges. By the time you get to 8, it would be 4, 5, 8. And then what's the last one? So the value of, how many are required to put 9 in its proper place? That's still in list 0. And again, you look at there's the 9. Well, how many values are greater than 9? And it's 26 and 27. Yeah, so by the time you get to the 9, this is all the first 4 values are sorted, but the 26 and the 27 are still to the left of 9. And one last problem, students. Number 2, suppose we have an array of 50 int values where the array elements are in descending order. That means you go from greatest to smallest. So that means as you go to the right, the next integer is smaller. So it'd be like, 100, 99, 50, 20. So you're guaranteed as you go to the next element, it's smaller. And then it says, suppose we sort the array with shell sort with a gap equal to 8. How many exchanges are required to place the value stored at index 41 in its proper place? Now you have to remember everything to the left of, because it's descending, everything to the left of the, there are 41 values because it's 0, the indices. How many values are to the left of index 41? Well, it's 41, right? The first, because we start counting from 0 through 40. So there's 41 values to the right of the number at index 41, and they're all greater. So let's say we call that, like in my solution, let's just let x be, I don't really care what the number is, it doesn't matter. So let x be the value stored at index 41, that's what I'm saying right here. But it didn't work out well. Oh, honestly, okay. And the one thing I know is because it's descending, everything to the left of, everything in indices 0 through 40 are greater than x. That's by definition of the problem because we're assuming it's descending. So how many, okay, and we're going to go 8 to the left. We move 8 to the left. So if we actually, when it came down to doing the exchanges, we would exchange 41 minus 8 is 33. So the first exchange would be 41 and 33, and then 25 and 33, and then 17 and 25, and then 9 and 8, and then the last exchange would be 8 and 1. And you can't go 8 to, so when that value is put at index 1, you can't go 8 to the left. There's no values left anymore. So we stop there. So we would take we take 5 exchanges. So whatever number is at position 41, it's going to take 5 exchanges to, let me start this again. We have this descending array of descending values, and we're sorting with a gap of 8. Okay, and so how many exchanges would it take to put whatever at 41 in its proper place? When the gap is 8, it would take 5. So I think that's a really good problem. And I'm not saying this, I wrote it, but I think if you understand problem number 2, if you understand all these problems, like the problems B, C, D, and problem 1, and especially problem number 2, then I think you have a good understanding of shell sort. And if you don't understand it, well, then I think you have this really great growth opportunity ahead of you. So, but I would definitely understand that before I take the test. Okay, so I think I'm going to stop sharing here.